It's the colloquium committee.
Webcasting is right.
Oh, okay. Yeah, we still have people coming in. I think we will wait for this. Oh, there we go. Thank you. So we are on already? Oh, Vina is testing the webcasting. Okay. Okay, so I think we're ready to start. There will be few more people coming in, I suspect, because we have a lot of registrants, and as you can tell, we had to close the registration early because we expect this room to fill up at some point. We are very lucky to have Eric Feigelson, Professor Eric Feigelson from Penn State University here today. And I can put this up. Okay. So these are the credentials of Professor of Astronomy and Astrophysics and of Statistics. That's Eric Feigelson. So Eric was a graduate student here at Harvard. And very recently I learned that he was studying radio galaxies for his PhD thesis, and he was working here in a group of X-ray astronomers. Professor Giacconi was here as well, and he was Eric was one of grad students studying X-rays, and I also learned that he was the one who saw the first X-ray jet in M87 and Centaurus A. So X-ray jets are very well studied now with Chandra, but the first X-ray observations were done with Einstein high-resolution imager, and Eric was one of the first people who saw X-ray jets. It was very nice to learn. Then he moved, after he graduated from Harvard, he moved to MIT and then to Penn State. In Penn State, he joined Jagush Babu, and initiated the, I would say, AstroStatistics field, and made a point of having us, astronomers, worry about statistics. So his conferences on statistical challenges in modern astronomy started in early 90s, 1991, and then they were very regular. Every 5 years, he put a group together of astronomers and statisticians and discussed the challenges at these meetings. I would say that Eric is one of the fathers of astrostatistics field, and made us all aware of how important statistics is in data analysis and in astronomy overall. Eric was also advocate of astrostatistics and initiated the groups at AAS, working group on astrostatistics and astroinformatics, and international astrostatistics working group as well. So right now we have a new established field where we see a lot of papers and a lot of development in that field. But Eric is also the editor of AstroStatistics and Astroinformatics portal, and this is where you can find the information about statistics and modern tools, computer algorithms. There is also a forum where you can join and ask questions, statisticians or astronomers who work on data. He is also a chair of this international working group in astrostatistics and astroinformatics. Eric reads a lot, and I think he's famous for actually knowing a lot and having all this information somewhere. And Tom Loretta once said that if he has any question, he just asks Eric, because Eric knows. So we are very lucky to have Eric here today and share with us all his knowledge. So I hope you will enjoy and ask questions.
Thank you very much, Annetta and Vinay, for making this happen. It's a little odd to have several hours of lectures by an outsider that are not research-oriented but are training. Okay, this is you're not going to get anything in cosmology or in stellar astrophysics from me. This is tools and ways of thinking about tools. So it's a little odd, but in fact, this material is not yet in the curriculum of the universities. It's not even at Penn State, and not at Harvard, and therefore, my coming here represents sort of an effort to promulgate ideas and methodologies and tools and software capabilities to students, grad students, young researchers, and to my wonderful pleasure and surprise, senior students, senior researchers who are also here. So I'm going to treat you all like grad students, no matter what your age is. And for my first hour, we're not going to do any R, but we are going to do R in my second hour this morning. So it'll be good if you have downloaded R onto your laptops, as Vinay has instructed. So this is what I'll talk about now. These are introductory comments, but in some ways, my introduction may be the most important part of the whole week, because I want to sort of change your mind view, or a common mind view, of the role of statistics in astronomy. I think most astronomers view it as just a toolbox, screwdrivers and hammers and wrenches, and you need to do something, and you grab a wrench and you do it and you put it back, and you've done it. Our goal, of course, is scientific insights, and these are just tools. And that actually is true, but the statistician would like us to be more thoughtful, more contemplative about how to approach a problem, maybe more varied in the tools we might use, and more judicious about evaluating the results. And they're actually surprisingly cautious and modest people. They actually don't believe their own results as much as we believe their results. It's sort of odd. Okay, so my first slide is sort of made for statisticians. It's what's astronomy, which is, of course, observations of stars and planets and galaxies in the universe from the perspective on Earth. And astrophysics, which has been the huge progress of the last century and a half, maybe, in bringing the laws of electromagnetism and quantum mechanics and gravity to bear. So we really understand enormous amounts of what we look at. This is trivial. We all do this. This is a great center of astronomy and astrophysics. You don't need that page. The point is, if you're going to talk about astrostatistics, that's astronomy, what's statistics? And then rather strangely, they don't know what statistics is. They're constantly debating this. So the great founder of 20th century statistics, Sir R.A. Fisher, said at this time he's barely out of his undergraduate years and laying the great foundations of likelihood theory. He says statistics is, in its most complete form, just the reduction of data. You have too many numbers and you want to reduce it down so you can just see them and sort of look at them. And if you look at Wikipedia, that's the first item. It's a mathematical body of science that's a collection and analysis of data. But they also add, well, there's interpretation or explanation. And this is actually a curiosity. I've been watching this Wikipedia page for several years, and they keep on changing this first line. Okay, so whether they really believe explanation's part of statistics or not. Okay, and D.R. Cox, Sir David R. Cox, in his late 80s, wrote in one of his early books really a different concept, a broader concept than just Fisher's reduction of data. A statistical inference carries us from observations to conclusions about the underlying populations. Now that really resonates with me as an astronomer because, you know, our galaxy has 1 trillion stars and there's trillions of galaxies easily seen. Of course, the universe is infinite, so there's an infinite number. But our samples are small. Even when we have 1 billion objects, it's still small. So what we want is to go from these observations. We don't really care about that Seyfert galaxy. We want to know about Seyfert galaxies in general. So we're very much interested in this inference process that takes us from observations to populations. Now, is statistics useful for science? Okay, and actually, bizarrely, in my personal opinion, the statisticians, the distinguished, are mostly pessimists. Okay, so George Box just passed away. He was Fisher's son-in-law and one of the great statisticians of the 20th century. Famously quipped, essentially all models are wrong, but some are useful. That does not resonate with me when I'm doing a binary star orbit based on Kepler's laws. I mean, I'm sorry. My model is not wrong. I know more than this. And the main problem is that Cox and Fisher and all those others spent most of their time with social scientists and human affairs, where they don't have physical laws. Okay? So C.R. Rao, the most decorated statistician of the 20th century, now in his 90s, quoted Osiander's preface to Copernicus. That you're not supposed to believe the meaning of the statistical result, okay? And then D.R. Cox, as an old man in the Principles of Statistical Inference, his sort of brief, sort of swan song at the end of his career, writes, the object of statistical inference is to provide ideas and methods for the critical analysis and, notice the caution, as far as feasible, the interpretation of empirical data. Even within data, he's cautious. The extremely challenging issues of scientific inference may be regarded as synthesizing very different kinds of conclusions, different kinds of data sets for different processes, and the use, if any, in the process of quantitative notions of probability is unclear. Now, in my opinion, the man's depressed. Okay, this is really just really not the way I would do it. So to find an optimist, I have to go to an astronomer, an astrostatistician. So this is Phil Gregory. I don't know if you happen to know him. He's a retired radio astronomer from British Columbia who wrote a lovely book in 2005. He's one of the Bayesian astronomers. And in his preface, he says what's really more what is called a positivist attitude towards science, but specifically on this issue of statistics and science. The goal of science is to unlock nature's secret. Our understanding comes from the development of theoretical models, like Kepler's laws, that are capable of explaining the existing observations and making testable predictions. So this is, classical positivist philosophy of science. Fortunately, a variety of sophisticated mathematical and computational approaches have been developed to help us through this interface from theory to observation. That's what that book is about. There's other things you can do with statistics. But from theory to observation, and these go under the heading of statistical inference. So statistical inference can, according to Gregory, work for scientists, particularly in linking data with models. Now, my personal opinion is this is the most important slide of my entire lectures for you for several hours. You may leave or go to sleep after this page, okay? this is what a statistician, these great statisticians, would sort of say to a scientist that they would meet, or a community of scientists, that you can reliably quantify information. Sometimes it's called knowledge discovery, that's buried inside of numbers, of data, of measurements. And if you want to, if you have models, you can help adjudicate the relevance of theoretical models. But it's just not straightforward. It's not like going in to a toolbox and taking out a wrench and turning it and putting it back. Okay? I mean, it has that element, but there's much. One is you should look at the data, as Fisher said. You should explore your data. And make sure you sort of see what's there. And of course, if it's very large and multidimensional, that exploration is not trivial. Now, this is very important. We would say, okay, I'll go back to when I was a grad student in the 70s and 80s. What's Hubble's constant, okay? And we had two great figures, one named Alan Sandage and one named Gerard de Vaucouleurs, who each had a sequence of about 20 papers in the APJ, one arguing that it was 100 and one arguing it was 50. Okay. But if you think about it a little more carefully, they actually weren't necessarily talking about exactly the same Hubble's constant. And they were using methods that were rather different, statistical methods, that actually were doing slightly different things and addressing slightly different questions. And you'll hear throughout my hours together with you that you'll see that there's often bifurcations. Do you really want to even do a regression? Because your scientific question may not have a response variable, or not obviously. Or if it does, you got to maybe think about it. And then once you've stated, your astronomers are often not stating them precisely enough to lead to the definition of which wrench to choose. Okay? That's one of the problems. And it's often quite difficult, and sometimes it's arbitrary, and communities just have to decide what question to ask because the scientific question isn't precise enough. Once you do that, then if there is a model, there isn't always a model, but if there is a model, then you have to decide, is it going to be a heuristic power law model, or is it going to be a model from quantum mechanics to explain a spectrum of an atmosphere of, let's say, accretion disk? What is the model? And this is, of course, where the astrophysicist comes in. And we are astrophysicists, and we're often thinking a lot about this, but sometimes we don't. We just assume it's a linear model, or we just assume it's something, and actually sometimes it's very heuristic and very arbitrary what we're doing. I'm not saying it's wrong to do exploratory arbitrary modeling, but we have to be aware that it's not necessarily, it may not lead to great science. The worry is the science depends on our choice of the model formulation, just as it depends on the statement of the problem. Then once we've done that, we choose a statistical method, and this is where there's a lot of meat. There's entire courses in for example, least squares, maximum likelihood, Bayesian are all approaches towards regression problems linking data to theory. And even within that, if you're doing maximizing a likelihood, do you use if you're an astronomer, you might use a Leverett-Marquardt calculation, and if you're a statistician, you use the EM algorithm, and each one of them has their own elaborations and their own details about methodology. And then you actually go to the computer and you calculate. And the problem is that too many astronomers sort of quickly breeze through these four earlier steps without thinking and slowing down and being pensive. And they jump in and calculate. They calculate something that, frankly, their professor told them to calculate, or the community has generally calculated, and just because it's convenient. And then they spend all their time coding these calculations, which is totally silly because they've all been coded by professionals. Okay, professors of statistical computing. It's a field, and it's all coded up. Unfortunately, the codes, as you'll hear, used to be private, commercial, but now there's public, and the R is the public code. Okay, it's used by all experts of statistical computing. It's the breadboard development environment for computational statistics. So this is actually easy. That's what you're going to learn. I'm going to train you in R, okay, and you'll train yourself in R. It's actually quite easy. And then you at the end get into this philosophical realm of D.R. Cox and C.R. Rao's pessimism, and I would say my own optimism, but caution. You got to be a little cautious about, not everything that's 3 sigma is right, and not everything that's 2.9 sigma is wrong. Okay, you have to think scientifically as well as mathematically to sort of end up with good science. You don't want your scientific conclusion to depend on arbitrary decisions you made earlier in the process. And if it does depend on it, you want to know that. Okay, so astronomers are not thinking enough. Okay, and that I think is the single most important thing that I'd like to say. When I showed this slide at Space Telescope recently, a senior astronomer came up and said, "I'm frightened. My whole career is dashed to the ground." And I don't think so. I don't think we're making lots of mistakes, even though I have a whole lecture at the end on mistakes. I think that we are maybe unwise decisions we're making. It's a question of quality. We do the most quality optics ever created by humankind. The most superb detectors. We do amazing astronomy. We know all of our stars and all of our galaxies. And we do fantastic astrophysics. So just why shouldn't we also do good statistical analysis? It's a question of quality. That's my personal opinion. Not so much where everything in the APJ is wrong. So I recommend this. And of course, the main problem is it wasn't in your curriculum, so you just didn't learn it. It wasn't so much that you're against this. Okay, just some random comments. Modern statistics since World War II has mushroomed like every other field has, so it's very, very vast. There's hundreds of books and dozens of fields, and you'll be seeing some of this today. It has a bad jargon problem, okay? Every statistical test has 2 obscure names you've never heard of, and you can't figure out what they do. And usually there's half a dozen ways of going from here to there, and you don't know which one to use, and it's a big mess. It gets very confusing. It's sort of, in my opinion, not very difficult. I mean, you've all done quantum mechanics and astrophysics. It's not that hard. It's not rocket science. And some of you are rocket scientists, okay? But it's big and confusing. And that's a barrier. It is a real barrier. Now, some of statistical procedures are based on theorems and lemmas, beautiful mathematics, which, by the way, I can't read. I'm not a good mathematician. And that often determines when you can do something and when you can't, or when a certain probability is valid and not. And if there is a theorem, don't violate it. Okay? Don't do anything the mathematician says don't do. I mean, you're literally doing something wrong that they know is wrong. Now, often, there is no theorem behind a thing. It's often called an algorithm or just a procedure, in which case you're on your own. But there are tools. One of them, a famous one, is called the bootstrap, that often allows you to evaluate the reliability of what you're doing, even if it's an algorithm without a theorem. And sometimes there are issues that are actually being fought over. I mean, there are discussions. I saw discussions between James O. Berger, the leading Bayesian statistician in the nation, and C.R. Rao, the leading frequentist, on whether to use which one of about 10 different model selection criteria to use that are based on likelihoods. And there was no solution to that debate. And that debate was 20 years ago, and there still is no solution. Okay? So you actually need to know that when there's a theorem and when there isn't. And it's very hard to know all that because there's a lot of education needed. Okay. Or you need access to experts. Astrostatisticians like Vinay, Anetta, and myself, who are specializing, or statisticians themselves, like you have at Harvard Department of Statistics. Now, this is my own idea. I just don't think that our science should depend on arbitrary choices. And if they do depend, we got to be very explicit that we're making what choices we're making. Particularly taking a log of a variable and then doing all sorts of marvelous things with the log. Well, that's a variable transformation. And you don't want your science to have depended that you took a log and not a square root, okay? Or something called standardized or Mahalanobis distances for multivariate standardized variables. So we have community habits which are not necessarily wrong, but be aware that your science may actually depend on some of these habitual choices. And one way around this is to just try things differently. And with R, it's very easy to do something 5 different ways. It's very quick, and it really, really works. Okay. And then what's the meaning? This is the philosophy, again, of Rao and Cox and others, and Gregory, okay, that your goal is to be a scientist and not a statistician. Sometimes a 10 sigma result, if you have 1 million points, may not be maybe a little 1% effect of no scientific interest. And if you have 20 points, you're unable to even find factors of 5 effects, okay? And so the probability isn't the p-value, it's sometimes called, is not necessarily the only thing to look at, and not just that. So we have to be knowledgeable, we have to study more and learn more, and we have to be judicious and not be sort of blindly accepting that every time we use that wrench, it's always perfect. Okay? So those 2 slides, to me, represent the philosophical issues of the statistician brought to the realm of astronomy. So let's now, I'm going to go pretty fast on this. Start off with the ancient Greeks and end up in 10 minutes, 2014, about the relationship between astronomy and statistics. So the ancient Greeks were very interested in knowing the length of the day, 365.25, da 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 da. And so Eratosthenes does it one way, and he made a bunch of measurements. Oh, Hipparchus, sorry, not Eratosthenes. He might have done it too. And what he did is he chose the longest year and the shortest day, and he chose the middle of the middle, even though there was no measurement there. And that's called minimax, and it is a method. It's not used today. Okay, it's not considered to be very reliable because it's very sensitive to one bad measurement at the edge. In medieval times, the theologians had a very clear answer. Observe something once and stop. Then you know the answer. Okay? So that's a very interesting approach. The mean of a bunch of measurements of a physically constant substance or phenomena was used by Tycho Brahe, was used by Galileo, but didn't really come into full use until someone named Simpson in the late 1700s. The median may actually be better than the mean, we would sort of say today, because it's more robust against outliers and non-Gaussianity, if you want to know the best value. And now there are estimates of the uncertainties of the median, which are not classical, but are available through the bootstrap or non-parametric statistics. Curiously, I don't have Kepler up there. I haven't done it, but apparently as you turn the pages of Kepler's notebooks, he uses the mean, the mode, the median, basically arbitrarily. He's basically confused, He doesn't know what to do. And of course, you turn the page and he has astrology because he's paid to do astrology and not astronomy. Okay. So Kepler, as usual, is an interstitial figure. Now, in the 19th century, things really changed. Newton's Principia was really digested in the 18th century, and by the early 19th century, they had this problem that in order to find the eccentricity and the semi-major axis and the parameters of Newtonian orbits from measurements of planets and moons and comets, they made multiple measurements, which of course had some scatter. Even Galileo has a wonderful discussion of observational error. Galileo's discussion could almost be applied today. Some of it is due to the poor observers that Tycho Brahe hired, and some of it has to do with other sources. What's the source of scatter? So to do this, some very great figures, Adrien Legendre, Simon Laplace, and Gauss. We think of Gauss as a mathematician, but actually Gauss spent most of his career as director of Göttingen Observatory. He was really he was like Charles Alcock, okay? That was his job. And everything they were doing and laying the foundations of least squares theory in the early 19th century was through astronomy. And the Gaussian error distribution was called the astronomical error distribution throughout the 19th century. And throughout the later half of the 1800s, almost every prominent astronomer participated in the mathematics of statistics. So it didn't take me very long to find a prominent astronomer whose name is Joseph Winlock, who was a young man as U.S. Navy Almanac Office, wrote a critique of the Royal Astronomer Airy's recent discussion of statistics. In one paragraph, he covers outlier rejection, autocorrelated residuals, and false positive and negative positives, all criticizing his British senior member of his community. And this gentleman happened to later become director of Harvard College Observatory, just before Pickering. Okay? So everyone was doing statistics then. The statisticians were the astronomers, and vice versa. So what happened? What happened was Maxwell and Planck and the understanding of physics, and people like Cecilia Payne, who was, just want to tell you something. I used to sit in this room, it wasn't as renovated as this, and hear, great astronomers of the 70s, and every once in a while, an old woman with white hair and a strange little cigar would sit in back. And we would nudge each other, we the grad students. Who's that? That was Cecilia Payne in her retirement. Do you remember, any of you, Cecilia Payne? Okay, so she was, to me, the symbol of the integration of physics and astronomy. And so we all became astrophysicists. For instance, the Center for Astrophysics. Okay, and the statisticians had another thing. They were discovered by leaders of industry and leaders of government, people who needed to collect taxes and recruit armies and get good crops and run factories. And so they entered in and also win elections. Okay, kings didn't need statisticians, but democratic leaders do. Okay, Gallup polls. Gallup poll. You sample 3,000 Americans. Will they vote for Mr. Romney or Mr. Obama? Astronomer. We sample 10,000 Seyfert galaxies. Okay, and there's millions of them out there. We have to make inferences about the underlying populations, just like the Gallup poll. So the statistics is needed for social sciences and human affairs as they are for physics. But the net result is that they broke contact. Even by 1916, Schlesinger said, please use least squares. People had forgotten to use least squares. When Zwicky discovered dark matter in the 1930s, he did it by eye, a fit by eye. He didn't use least squares. But Hubble did, 1930. Hubble used least squares. So it was like we were forgetting our heritage and this particular aspect of our heritage. So the net result is by the time I came along in the 70s and 80s, things were pretty bad. And actually, I hate to say it as an AppJ editor, I'd say the median paper coming into the AppJ is not very impressive. Okay, typically we're using rather old techniques and sort of pre-World War II techniques and sometimes pre-20th century techniques. And I'm not against them. They're not bad, but they're not always the right tool or the effective tool. And sometimes it's even misused. And so I've developed a whole lecture. You're going to be the second audience ever to hear it on Friday of the misuse of some common tools. And we'll see if you like that lecture or not. I don't know. It's a little, I don't know, aggressive? I'm not aggressive. I'm trying to improve things. Okay. My own personal emphasis in my own sort of teaching and culminating we're going in our 10th year of summer schools at Penn State, 1 week summer schools, and culminating in a textbook from the summer school, and really the tutorials are from the textbook from the summer schools, is to say what is available in likelihood theory, Bayesian information criteria, and Bootstrap. These are very important for linking data with models. Multivariate classification started in the 1940s by Fisher with linear discriminant analysis, developed into support vector machines and classification regression trees and random forests. And if you don't know these things, then you shouldn't be classifying. This is incredibly heavily used. All of those techniques are used by tens of thousands of researchers in other fields and are rarely used in astronomy because of the breakage we had between the fields. In time series, there's a lot of options beyond Fourier analysis. In spatial point processes, they don't use the two-point correlation function. They use the integral of the two-point correlation function, which is called Ripley's K. And if you don't know that, then you can't do it. If you don't know that geostatisticians invented something called Kriging, then you don't realize that Gaussian processes regression has been around for decades. And I myself sort of discovered, along with Jürgen Schmidt, also a grad student here, that survival analysis can help with the astronomical non-detections. For image analysis, we should be reading the literature from the engineering community because they have a heck of a lot of CCD images in engineering. Think of every security camera in the world. Think of the agencies that are paying to analyze them. So they know a great deal about the image analysis and data cube analysis. And for things, there's a new technology called false detection rates. And for computing, we don't know about R. And R has been strong for a decade and dominant for half a decade. So we're not that late in R, but it's really useful. And that's the purpose of today, of this, my being here. That's the purpose of the textbook. This is my own personal niche of where I personally I want to educate. Established techniques that are generally unfamiliar to many astronomers, who, although they may know some of it, but unlikely they know all of it. And this page is not really meant for me to read. It's just an attempt to take one field of astronomy and to sort of look at some broad questions that are in there, and to see if I can just sort of connect it almost as a vocabulary lesson to a statistical field. For instance, if you go, just a trivial one, if you go to any statistical textbook and look up the word power law in the index, there's almost nothing there. So you think they haven't done power law relationships. Well, that's because it's called Pareto, from the founder of modern quantitative economics in the 1890s. He did the work on the power law relationship, and so it's called the Pareto distribution. And if you look that up in the index, you find there's an enormous amount of mathematics over about a century on how to do it, and also how not to do it. Like, don't bin the data and then fit up these squares to find your power law. It's a really bad method. And they've known that, of course, since the 1950s. And some of us know it and some of us don't. So this is just an example of the kind of things which collectively we really need to know, this sort of stuff. The Schechter luminosity function should never have been called that. I'm sorry, Paul. It should have been called the gamma distribution. It's been known since the early 1800s. We did not invent it, and there's a great deal known about it. Now, the good news is that things are not always so bad. Things are improving. We now have R and CRAN. Python is improving. Python is still an order of magnitude smaller than R, or at least, probably more, but it has a lot of really good stuff. IDL has not so great, but it has some. There is a lot of research going on, okay? The papers in the astronomical literature that say method statistical is doubling on a time scale of a decade. To quite a sophisticated number. So we're doing statistics in the appendices of the Astrophysical Journal. There's training courses. We give, one way or another, these training courses around the world the last few years. And most impressively, there are people, and that's not including me, who push the envelope, who already know existing methods and are really challenging and developing new methodology for important astronomical problems. One of the oldest and most famous of these collaborations is right here at Harvard, started 15 years ago, supported by Harvey Tannenbaum, director of the Chandra X-ray Center, and Vinay and Aneta are two of the senior members of this team, and they've worked with statisticians at Harvard, or former members of Harvard as well, particularly David Van Dyke, who's now a co-director of the Imperial College Center of Inference and Cosmology in London. Carnegie Mellon has a collaboration. We have a collaboration. There's one out in Silicon Valley. France has a superb collaboration. Cornell has a collaboration. Berkeley, Michigan, etc. Notice these are rather impressive universities. Okay, secondary universities don't have astrostatisticians, but some of the leading universities do. And we have conferences. Annetta kindly mentioned that we've been running a conference every 5 years at Penn State. They were really bad at the beginning because the statisticians astronomers didn't know their languages and problems. Now they're much better. The physicists run some that we're invited to. There's a wonderful institute called SAMSI in North Carolina that's like the Aspen Institutes, but it's cross-disciplinary, and they bring in astronomers and statisticians, or bring in many scientists, scientific communities, and statisticians to work, and applied mathematicians to work together. And now there's a new trend of conferences in astroinformatics, the methodology of computation. And particularly as we go into the big data world of petabytes and exabytes, this becomes critically important. And it's sort of threaded in with statistics. It's not really the same. There's different approaches. But it actually, to be very simplistic about it, the statistician tells you what to compute, and the informatics expert tells you how to compute it. So you can't really have one without the other. And they're importantly intertwined. And finally, we have these new, you saw this list. I think there's been perhaps a little too enthusiastic a profusion of organizations. Every leader of every international organization wants to have an astrostatistics group. So not only these, but the ACM is talking about it, and the American Statistical Association is talking about it. But by the end of 2015, there's going to be like 6 of these organizations. I'm not sure they do much. I'm sure of one of them. I'm not sure we do much. But the point you should get out of it is that there's a lot of momentum right now. That statistics and astronomy are no longer in the cold away from each other. They're in a warm room, and they're talking together. And textbooks are helping. Ours is just one of them. Wallen Jenkins has been around some years. It's now in 2nd edition. Phil Gregory's on Bayesian. And a brand new one I want to recommend to you is a Python guide to statistics and data mining by a very fine group of astrostatisticians at University of Washington. If you don't happen to know, these people are leaders of LSST. So it's really good that the project scientist of LSST just wrote a book on statistics. I mean, this shows a lot of progress, okay, in the field. So this software and textbooks, without that, you can't proceed. There's too much to know. Although, actually, Wikipedia, I could put in here. Wikipedia is surprisingly good for statistics, but it's still incomplete. Now, I'd like to advertise, since I am chair of one of them, the first IAU conference in history that is on astrostatistics is occurring in Lisbon in May. It's on statistical challenges in cosmology. You're very welcome to register, and registration's now going on. And then this portal is available to you. These are we have 1,500 recent papers, all searchable in this little window right here. A lot of web resources deep inside. This is 3 levels deep. Not many articles. The forums are sort of moribund because astronomers don't ask enough questions. The meetings list is pretty impressive. And so Joe Hilby and I run this site. Joe is a senior statistician. So ladies and gentlemen, that is my, I'm actually going to ask for comments at this point. That's my first talk. That's called Introduction to Astrostatistics, from philosophy through history to the present. And are there any comments? And then what's going to happen is my last 15 minutes, I'm going to introduce to you statistical computing and the background to R. Okay, which is more practical. But this was more conceptual. Any comments or questions?
What's the category for something like
XSpec.
Yeah.
It's a disciplinary DSL something language. We have programs in astronomy. Let's say GalFit for morphology of galaxies, XSpec for modeling spectra of X-ray sources, and a wide variety of others that are fairly seriously maintained over, version 3.11 or something. And these have embedded in them statistical methodology. And every pipeline of every instrument, inside of it hidden away, is methodology. There's choices going on of, what do I do about the outliers? And by the way, outlier rejection is an entire field of statistics. I mean, R has, 100 packages just on robust methodology. The word robust means outlier rejection. That robust doesn't mean, I feel robust today. It's a technical word. They use English badly, in my opinion. They use regular English words to mean technical things. So robust is what we would call dealing with non-Gaussianity and that. So there's a lot of statistics deep inside of astronomy, and some of the authors of these pipelines and packages know a lot of statistics, and some know some and some know little. I would say none of them that I've met know a lot. So I happen to know Keith Arnaud. He's been to 2 of our meetings. He's no fool, okay? But yet, when I asked him to put the BIC into it, he wouldn't do it because he thought it would be misused by astronomers. So I thought that was unwise because, tens of thousands of other researchers know how to use the BIC, Bayesian information criterion. It's a way of judging between 2 models, applying Occam's razor of parsimony in model development for nonlinear functions, nonlinear models. It's very important for us. So I think he should have done it and just linked to the Wikipedia page on the BIC. So Keith didn't do that. Or if he did it recently, I don't know. So sometimes, otherwise I love Keith. so there's an example. I just happen to know, Ed and I know, we know that.
Application of the things you've been talking about.
Yep. I would say the next generation of pipeline writers and of people who write specialized codes should consult with astrostatisticians and statisticians to make sure they're doing a reasonable thing. Okay, there's a lot of in radio millimeter astronomy to find a cloud in a data cube they use something called Gauss clumps, and Gauss clumps is a least squares technique when in fact it's been advocated for 40 years to use a maximum likelihood technique, and it's just more stable and more informative and not necessarily, astronomers are a little behind the times. Sometimes they're very far behind the times, and we'll get to that on Friday. Any more comments? Sir, ma'am, yes, Netta.
Yeah, when you were talking about the history of statistics, there was this medieval times when you had one observation.
Yes.
That's what we do in astronomy sometimes, right? You just have one observation in Chandra.
Right, well there you are, you have $1 billion telescope, and you fought 10 to 1 to get an hour of time on it or a day of time, and you have one observation and you're stuck, that's it. And I agree. But as a field, that isn't true. If you're studying globular clusters, you probably studied other ones earlier, or your competitors did, and others will study others in the future. And so as a field, we are really quite good, I think, in developing sort of the science derived from samples. But you're completely right. We often struggle right up to our noise because it was so expensive to acquire the data. And I personally feel that it's important that codes like Chow and Sherpa, and that happens to be X-ray astronomy, that we're both involved in, be sophisticated in these respects. Scott.
This is just kind of a prelude, I guess, to where we're going. But one of the other issues is not only do you only get a single observation often, but you often are dealing with a phenomena you know is time variable, and you suspect might be time variable in conjunction with a phase or some other physical constraint that you are imposing as a prior sometimes when you do the statistical analysis. And where I run into the biggest trouble is saying, okay, I impose my prior, I say that I think I'm looking at a phase-dependent phenomena, and that gives me a, quote, better statistic, end of quote, and then I'm in a position where I can say, okay, therefore my prior is true, which of course isn't true.
No, right. Okay, let's reserve this in more detail for Friday, where I have a discussion slide or so on the advantages and the risks of using Bayesian approaches. That's the word prior that Scott is using. But actually, if you took a frequentist, if C.R. Rao, a distinguished 90-year-old Indian, were here, he would not be fazed by your question that, oh, your objects are variable and very confusing. He would say, he says in his book called Chance, and I forgot, his autobiographical book on the concepts of statistics, he says, statistics is to quantify uncertainty. And if you have variability in your phenomenon, that's exactly what statistics is designed to deal with. So they're not fazed by, well, let's just call it lousy data. Okay? That's exactly what their math is designed to address. What can you reliably infer from lousy data? Yes, Vinay.
Just following up on these two questions, actually. So, if a frequentist encounters one observation, how exactly would they do that?
Let's not get into that. Okay, it's important not to exaggerate, to know what the word reliable means. What you can say reliably. You can always say, I measured 11.35 magnitudes. I measured it. It's reliable to within 0.01 magnitudes. I did that. At the same time, you may say that I can't infer much about my scientific question from that. So, because it's just one measurement of one object that's probably variable and doesn't tell me the spectra, and I'm just not going to learn that much. I think issues of caution, both statistically, mathematically, and scientifically, are important. But we're pretty good at scientific. We write these discussion sections to our papers that if we don't, the referee and the editor demand that we evaluate how reliable it is. So we don't exaggerate our findings. And we're pretty good at that. Okay, any last questions or comments? They are much more philosophical about what they do than we are. I found that to be strange. I always thought statisticians would be really boring people. And they're not. They're not. Okay. Statistical computing is a minor subfield of computational science. When computers came along, IBM mainframes, one company, actually two or three companies, there they are listed. SAS is the big one. SAS is the largest privately owned software company in the world. There's an entire city in North Carolina of statisticians that run SAS. It was made on IBM mainframes and then went to Windows after that. And basically the statisticians would develop methodology and SAS would implement it in a Fortran-like language. And that's the way things ran for decades and decades. And you would then spend a fortune as a company to buy SAS. And for some reason, astronomers decided to spend a fortune to buy IDL, but not SAS. And well, there were reasons, but the net result is we never knew what was in SAS. So we never knew what the statisticians had because IDL didn't bring it into IDL. Okay? And numerical recipes is extremely, it's good, but it's inadequate. It's a big, thick book, but only that much is statistics, and that's not enough. So it's gotten a little thicker in the later editions. So we didn't know about that, basically. Now, in the 1980s, C was invented at Bell Labs, and one of the young people there, he's now emeritus at Stanford, John Chambers, developed a software system in C, written in C, that was extensible in C, or a C-like language. It was called S. And any of you ever use S or S+, just in your younger years? No, okay. Actually, a few of us did. Keith did for years. But it wasn't that popular. And it's a commercial system. It costs money. In the 1990s, two statisticians decided that the GNU public license system was emerging, that they would write a statistics package in the public domain, and they decided to mimic S. So they rewrote the foundations of S in the public domain using sort of a combination of C, using in C, actually. And then S grew. They brought in friends who were professors of statistics, and they opened it up for users to contribute to it, very much like it became called CRAN, the Comprehensive R Analysis Network. I forgot, it's based on 10? I don't know. They mimic some other system to allow users to add on packages so that the system could grow more than the statisticians themselves could write. But they do the base R. So that was early 2000s that this really started emerging. And then to everyone's total flabbergasting, they were just amazed. This is a log plot on the y-axis of the number of packages contributed to CRAN and a linear plot in time from 2001 to the present. And it's a straight line. It's been growing exponentially from 2001 to 2013, and finally it seems to have come off the exponential, which, of course, things can't grow exponential forever. They really can't. But the net result is sort of by 2008-ish or something, R and its add-on packages CRAN became really big. It's now, no one knows, but it could be bigger than SAS. No one knows how many people use it. The estimate a few years ago was 2 million people use it. All we know is that it's huge, it's vast, it's used by hundreds of thousands of people, and particularly certain communities. Genomics, the statistics of 4 letters, right? Cytosine, guanine, adenine, thymine, right? All the sequencing is very statistical. They don't just sequence it directly. It's all done by statistics. Since that emerged roughly the same time R did, it's all in R. So they have 500 packages at least in genomics called bioconductor. And economics, econometricians use it. Those are the people who messed up our economy in 2008. They're very smart, but not always wise. and they have hundreds of packages. And then everyone else does. And many of them are of general use. So here's the latest census. This goes up about 50 a week or something. No one knows how many functions there are. A function means what you and I would call a subroutine, like the median, there's a function. A support vector machine of 1 million objects in 30 dimensions, that's a function. So you call each of them in one line. So you can call in one line this incredible, amazing apparatus, or you can call something simple, and they're called functions. So nobody even knows how big it is because no one counts. There's no company behind it. There's a bunch of stat professors who are not paid. I mean, NSF sort of slips them some money, but essentially it's not a system. So this surprised everyone how big it became and how useful it's become. But please be aware, it is a public, user-supported enterprise. In other words, there is no company behind it, and it therefore lacks some coherence. Okay, but then that's true with Python. I mean, there's a core of Python that's solid, but people add stuff on it, and well, maybe it's right, maybe it's not. Okay, so it integrates data manipulation as everything IDL does. Okay, it's very much more like IDL than Python. You'll see, of course, starting in a few minutes. Has a lot of graphics. Both in base R has good graphics and it has wonderful add-ons. Of course, the main reason to use R is statistical analysis. Okay. Has uniform documentation. You'll see some of it, but it's very sparse. It doesn't teach you. It's not didactic, but it's very useful. And it has uniform coding standards. But no one knows, except for base R, you can't be guaranteed the answer's right because it's user supplied. It's fully programmable, C-like language. You can do it. We'll do a little bit of it in the next couple of days. You download it in a couple minutes. How many of you have downloaded R onto your machine? Okay, there we go. That's everyone. And you might say, well, how do I get my 5,000 packages? And the answer is you get it on the fly. We'll do it. We'll do it together. It's really cool. It's just amazing. And of course, it's the packages that really make it. It would be a mid-size, high-quality system without the packages. But with the packages, it's just wonderful. It has enormous numbers of resources out there because there's several million users. There's a basic manual of all the functions in base R, about 3,000 pages. Every CRAN task has its own manual, but there's so many of them that there's actually got to look at task views just to find them. And the vignette files, there should be more of them, but they should insist on these. These are the useful manuals, and these are the help files are sort of too short. But there's a lot of tutorials. We're not the only people doing tutorials. There's gobs of them. There's a book a month coming into the Penn State Library with R in the title. A book a month. Springer alone has a series called Use R, which is, I think, up to 50 books, and there are dozens more coming. I mean, it's big. There's blogs. Some of them are huge. Some are small. There's conferences. There's galleries. There's companies. They actually try to make money even though it's free, and there's true journals. Okay, so it's pretty hard to use, not because it's hard. I mean, it's not. You're going to find it's easy to learn R. Okay, it's hard to. The hard part is knowing what you want to do, and then the next thing is finding what you want, which is not that hard. I just use Google, or I could use RSeek, but I just Google it and find what I want, and then I write my script, which is not that hard. It's like writing IDL scripts, and then understanding what you find, and that's thoughtful. Okay, that's the first and the last are the thinking, and the middle is the doing, and it's much easier than it used to be before R. So here's a page that lists sort of some categories of things in R. Each one you might think of as a textbook that you can get in your math library. Many of them are for sale to students at your local Barnes & Noble or your Harvard Coop. So, you know, there's books on robust statistics. There's books on bootstrap resampling. And so each one of these is a category that is as big as a textbook. and it's huge, okay? That's a nice list of things that it does. And that's not complete. And then it's absolutely impossible for me to give the list for CRAN because there's 100,000 of them, and last time I looked in great detail of it was well down on the exponential curve, so it's grown a lot. But here's just, I started with B and ended up with W. It's alphabetical. It's not meant to make any sense. But let's just look. Wavelet is a dozen wavelet toolboxes. One of them comes from the Stanford group, brilliant group. Others, maybe some grad student somewhere put in one or two functions. You can't really tell ahead of time how much it is, okay? So it's very complex. We often want to know, are there two kinds of objects or is there only one? That's multimodality. That's actually a difficult question in research level statistics. And it's not sort of fully settled how to do that. And it's not obvious. There's neural networks, several packages available, large and small, authoritative and less authoritative. And yet neural networks is only one way of classifying multivariate data. And Bayesian, there's dozens of MCMC packages as well, including a connection to bugs, which is the original package. So this is how you find some stuff. CRAN task views, you say CRAN task views, and then you add your nouns about what you're looking for. And you can see, look, time series, 140 packages, machine learning, 70 packages. It's just huge. Now, this is very important. I'm running out of time. It's interfacing bidirectionally with Python, with Fortran and C and Ruby. You can sit in Python and call your 100,000 functions. You got to wrap it. Or you can sit in R and call your C program, which is very important because C is often faster than R. And that's been done for decades. The computationally intensive stuff you rewrite in C or Fortran and you call it. And the statisticians live in R and they call C. But we can live in C and call R. Or live in Python and call R. And this, I think, is going to be the future of us. Because R was sort of designed for a single user to sit at a workstation and sort of fuss around with their data. But we have legacy codes, we've got pipelines, and we often don't. I mean, we can operate that way, but eventually we want to write our own code in our own world. And so I think we're going to use R in our world. And that's not commonly done yet. It's fairly rare. Okay?
What about IDL then?
No, IDL's commercial, proprietary. They share with nobody.
But you can't.
We're right now finishing up a translation of astrolib routines into R. You know, the stupid formatting of RA index, that kind of, the underlying infrastructure of astrolib. Not all of it, but some of it, 100 routines roughly. So, but no, IDL's quite uncooperative with everybody. Okay, they're making money. And they're not innovating as fast as everyone else. So it's time to drop IDL. And just look at the graphics, it's huge, okay? It also has close connections to LaTeX. You can write documents that actually run our code, that use your updated data sets and stuff like this. Basically, it's the premier public domain statistical computing environment for some years. Okay, I think I'm going to stop there. I have a few more slides, which I think I'll start in a few minutes. So thank you very much. Now, I have a comment on R or statistical computing.
There's the general comment, you get what you paid for.
Yes, and that's
So
true.
That's always
That's true with Python. It's true with R.
Exactly. So
Yes.
you have those packages, people have develop them. And then once they go into a large production, they break.
Yes.
Because they're not designed. R and Python were not designed from the ground up for high performance computing. You know,
Yes.
I'm dealing with the genomics people trying to run on a cluster.
Yes.
You know, they want to run R and it's, you know. and
Okay,
they-
R has 60 packages written by computer scientists to try to make it high-performance computing in a variety of ways. I can show some slides on that if you want. But my own opinion is not ready for prime time. I mean, some of them may work, but they're not integrated together.
That's really the problem.
That's-
And the other is if you have.
But it's not
if
black
it-
and
if
white.
If it's,
Sir,
yeah, but you have to be careful. What is the quality at the end of the tool you're using?
Right.
And you may say, I'm not using the right statistics. The problem is that the tool you use was not written right. And
Okay.
how do you go around that? And
have
don't
to be
get me
thoughtful.
wrong, I have a lot of issues with IDL, you know, but you can tell them, I paid for it, you should deliver. While you download, you know, some package from R that comes from a grad student, and he's gone out, he's gone to something else, and you realize that something was not coded right.
Right.
How do you deal with the fact that, you know, you've
But-
claimed that you've done the right statistics?
But we have to move beyond 1930s methodology. So we are in a bind. We have to struggle to use modern methods, learn and use modern methods, at the same time live in a software environment where, I mean, if you really want to do it right, you should buy SAS. The FDA requires SAS output before it approves drugs. Okay, thanks very much. So I think we're going to have a few minutes break. Vinay, do you want to say what we're going to do? And then I'm going to come back in a few minutes.
No, we can take a 5-minute break and then come back.
5-minute break. There's some snacks, and of course there's bathrooms. Whatever you want.
Broadcast, but some people are having problems.
Vinay, are you here? Well, you raise your hand and Vinay will help you find this page. Is that good? Yes? Okay. And if you're on the webcast, you'll just have to find it. Apparently, there's a CFA page that Vinay has provided this. Okay, I'm going to show a couple more slides about R, and then we'll go directly into it. Okay, just some features. Obviously, it's a big system, but just some comments, really. Originally designed for individual use on a workstation with interactive. It's made for you to explore using many methods, but it can be pipelined, and you'll find out that the experience, the language is very much like IDL. In fact, you can translate IDL into R and vice versa very easily. It has a little bit of object-oriented language sort of built into it. It's not a pure form of it, but it has classes like numeric objects. They're called objects. Numeric character, logical vector, matrix. Factor is like categories. And we'll see a data frame in a few minutes. A data frame is a matrix with the names of the columns. That's what a data frame is. A list is like a bucket where you can put heterogeneous things in a hierarchical fashion of all the other types of the things. It's very much like an IDL save file, if you happen to know what that is. And then there are a lot of other classes that an individual function is allowed to make a class. So LM, linear modeling, creates an output, a list typically, of class LM. And this means the reason for doing that is that then you can plot. You can write the word just plot the output of these different classes, and there's dozens of them, or print or summary, that are closely adapted to that particular. You don't have to dig inside the list, although we'll show both the simple version and the digging inside as well today and on Friday. There's a lot of graphics, several GUIs can be done. There's some galleries here with thousands of examples, mostly from the social and biological sciences. Now, some computational things, it can be quite compact. This is a little example of filtering some velocities and then asking where the 75th percentile is. This was done by Bill Press in talking about numerical recipes and comparing Fortran C and IDL. And here it is all in one line of R. So this is, Fortran's about 10 lines. IDL is 2 lines and creates some intermediate quantities that aren't, and R is 1 line. And that's because you can embed inside of R functions inside of functions, and also you can filter very easily. And it has some specialized things for statistical analysis, like quantile. It's designed to do vectors and matrices very fast. It's just like C. On my little laptop, I do 1 million element FFT in 1/3 of a second. It's very good at random numbers. These are fully professionalized applied mathematics. It's not written by amateurs. It's modern, high quality stuff. There's half a dozen random number generators that are new, and if you don't like them, you can put in your own. But if you want to do, let's say, a do loop, as we'd call it in Fortran, or a for loop, as it's called in R, it's very slow, because you're going in and out and in and out, and linear modeling creates 2 copies in the original of your data set. And there's certain things that are inefficient in R, as it was originally designed. And some things have been sped up. It now has a compiler that goes as fast as Python and Java. Originally, it had a slower compiler. And some of these things have been sped up. This speeding up only occurred last year. And then, again, on computational aspects, there are high-performance computing sort of packages that you then use together with other functions. When you have something that's computationally intensive, it allows you to deal with data streams, with data on a disk, with data on a cloud. It allows parallelization with heterogeneous GPUs and CPUs, or one or the other. It follows some of these standards of high-performance computing. And so it looks really good. My own personal opinion is it's not clear to me. These are not integrated together in a clear way, in my opinion. But most of these packages were written by computer scientists who basically said, oh, look at R. Sometime in the late 2000s, they said, hey, look at R. Let's see what we can do. And so it's sort of becoming more computationally better than it was. Now, at Penn State, we have a web service to 50 simple functions. It's associated with the virtual observatory using the SAMP protocol. We run these summer schools. We have a textbook. We run the portal. And we're writing an AstroLib and a CFITS.io and maybe some other infrastructure packages. So that's just a comment of what we do. I really like R. I think it will be a very effective add-on to, let's just say, Python or whatever your other favorite language is. You might live in both languages because R has real advantages. There's entire discussion of Python versus R by the professional data analysts, and the answer is both. The answer is they each have a great power and effectiveness. Okay, now is our chance to start R. And I apologize to those of you who already know a lot. This is going to start off elementary. Where is my R? Well, I've lost it. I'll start it up. Oh, I really lost it. It's probably off my window somewhere. Okay, so I'll have to find it.
Question?
Yes.
Should we use the command line R or the...
It makes no difference because as soon as the very first thing when you either double click or type the letter R is you immediately get the console. So it doesn't matter at all. Linux is command line and Windows and Mac OS is double click, is an icon. But it doesn't matter in the least. It immediately brings up the R console. See the word R console on top? That's your environment. R console. I believe that's the same in both of them. Okay. So the first thing is, where are we? So we're going to say get working directory, get WD, and I'm sitting there in my sort of upper level. Every single function in R has parentheses. If there are no parameters, then there's parentheses with nothing in them, as it is with this one. So I'm going to set my working directory, and you should set yours. You can live in your one you have. I'm going to set mine in the CFA 2014 directory that I set up, using set working directory. Notice I use quotes. And now I'm just going to, I don't know, learn a couple things about what I'm doing. I'm going to type a function called session info. It's telling me that I'm using a version of R from September 2013, so I'm a few months old. You probably have one from yesterday. It's updated daily. It tells me I'm using Apple Darwin, and this is some other stuff. It's telling me what my basic base is the package that has most of the basic R in it. But as you bring in more CRAN packages, they show up there. And one thing that I think it's courteous that we do, but also eventually important for reproducibility, is we cite R in our journals, and we cite every CRAN package using the citation command, citation function. So the author of R is R core team. And then you put the year 2014, and the reference is R Foundation for Statistical Computing, Vienna, Austria, and there's the URL. And that's how you reference R in your AppJ paper. Okay, let's create ourselves a vector. We're just going to do some math. We're not going to use real astronomy today, in this very first hour. So we're going to create a vector using the C function. The C function means combine, or you can think of concatenate, and it's separated by commas. And whenever you have an object, we can just see ls lists the objects I have, and I have an object called A. I just created it, and that you can use an equal sign, but for some technical reason you're not supposed to. That's the assign function, not function. It is A, and that's a less than hyphen or equal sign, and so we're assigning this on the right to that thing on the left, and this assign operation is crucial. And there it is. It's now created. If I want to look at something that's already there, I just type it. I don't have to use the word print or anything like that. I just type A, and there it is. there's the content of that object. It could be very big or very small, depending on the situation. If it's a vector, I can ask how long is it? So I'm going to ask length. By the way, it puts in parentheses, close parentheses for you. Also, the up arrows and down arrows work. You can go up and edit a previous line and nice things like that. These entire environments, such as RStudio, to do R development and brings up an R console and an R development window and versions. And it's very beautiful, but I'm not going to do that. We can ask, what's the class of A? It's a numeric. We can ask, what's the structure of A? And for more complicated lists, this is where you learn what's inside of a list, is to use str for structure. I think the equivalent IDL might be help. And I can write it onto my disk, file equal output, quote, output A, oops, space A. Okay, it does put in this thing. Oh, it did something. Let me go and look. Where is it? I gotta go inside. That's funny. Output, there it is. Today at 10:23 a.m., a file was created called output, which has 4 numbers in it in ASCII. Okay, my write command worked. That was, R tends to think in ASCII because, I don't know why, social scientists and statisticians, but of course we often think in binary, so we can just say save, and that will save it in binary. And then I want to show you something that I did the save command using a capital S for save. And I have an error. It cannot find a function called SAVE capital S. And that's because R is case sensitive, which is a pain if you don't know ahead of time what the case is and what you're doing. Because people can do any cases they want, and some people do just odd things, and you don't necessarily know. Okay, we have a vector. Let's characterize it of some very traditional things you might do with a vector. Let's say what's the mean and the median of the vector. There we go. 56.75 is the mean and 51 is the median. If you know, there's only 4 numbers here. It actually took the mean of the inner 2 numbers. That's the definition of the median for an even numbered vector. I can ask the min and the max. I can ask the sum of it. And now here's something a little more interesting. I did the sum of the values of A that are greater than 40. And so I'm allowed to put in filters inside of functions of this type. Yes? Yeah, I'm a little surprised.
That's because you've done A greater than 40 to type in, it's like true, false, and when sums that
Okay.
true, so you have to put like A square brackets in.
Right. I inadvertently created a logical. Thank you so much. So I didn't really do the sum. I summed a logical. Thank you. I had not realized that till I just saw the 3 here. Now, there's prints and summaries for many, many classes. So here's an example. If you do a vector, what summary does, it tells you 6 important numbers, the min, the median, the mean and the max, and also the 2 75th and 25th quartiles. And that's often useful to just look at that. And you can say, you can ask sort of what are the indices of things. So what's the index of the maximum? And you can match values with elements and find out that the second object matches the value 44. You can filter using square brackets, very commonly done for vectors and matrices. So I'm going to print out, in this case I just said A, carriage return. Oh, well, the semicolon is a carriage return. It's just more compact sometimes to just put 2 small things on one line. There's no meaning to it. It's just a carriage return. So this is all 4 elements, 1 colon 4, and this is the third value, the element of the object at the third index. It's the third number in the vector. If you have a matrix, you would use a comma to separate the dimensions. Yes?
It starts to 1 and not to 0.
Yes, that's right. Thank you so much. That's extremely good. IDL vectors start at 0, and in R, they start at 1. I wonder, A bracket 0. That's funny. It didn't crash. I wonder what numeric 0 means. I don't know. I don't know what it did. I don't know. Sorry. Okay, let's make a data frame. In this case, I'm going to use that assign operation, and I'm going to use a function called data frame, also known as data frame, and you can change between classes using as dot something or another. And now this is a little interesting. We're beginning to actually do something here. First, I've actually embedded 3 R functions on the same line, which is inconvenient for reading, but is convenient for writing. No, I mean, if you're smart, you can just pile them in, but it doesn't lead to very easily readable code for outsiders. So let's start on the inside. First, I ran something that was a SEQ, a sequence. And I made a sequence of, in this case, integers from 1 to 4. So this is made a vector. And then I had a 4-element vector over here called A. And then I did column bind, C bind, column bind. I put the 2 vectors, column 1, column 2, and made a matrix out of it. And then I put the matrix into a data frame, which means it's waiting now for the names of it. And so I can now add the names as ASCII names. Again, I've assigned it. I've called them rows and values. And now I can say, well, what do I have? I have df.a. And this is a data frame. IDL's favorite sort of thing to look at is a table. A table with 1 column or 100 columns with, 10 lines or 1,000,000 lines. It doesn't care. Okay, there's no maximum array size other than the size of your computer, hardware limit. But it likes to think in terms of tables. It's not the only thing it can think about, but it often does. It often translates other structures into table-like structures. Yeah.
Is there any reason that you use the dot A for that?
No, I can do anything. There's something they don't like underscore, but I've used underscore in names and it works fine. I think there are some rules. I think dashes are forbidden. It will tell you if it doesn't like it.
One question about the sequence thing. What
Yeah,
does the sequence exactly do? If I do sequence 1, column 4, it gives me the same as sequence 2.
Yes. Okay. Let's now say you either see some script or you want to develop a script, and you don't know what SEQ does. So you say help, parenthesis, SEQ. And this is absolutely crucial. First, you are young R users, but even experienced R users are looking at these one-page help files all the time because there's no way to know what it's actually doing. So let's now look carefully. That was a great question. You led up directly to what I wanted to do. Let's go look at one of these help files in some detail. Okay? And literally, you should be looking at your help file of every single function until you get the hang of R and then keep on using the help. I use them all the time. Okay, it's called SEQ and it lives in base. This is where the package will be listed. This is the name of it. SEQ is sequence generation, and the first thing is a 1 or 2 sentence description. Generates regular sequences, blah, 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 blah. Okay, regular sequences. Usage. This is now going to tell you your input options, basically. So there's a from, a to, a by, or a length, and an along with. And then there's some options here. And now it's going to tell you arguments, the inputs to the function that go inside the parentheses, and it tells you what they are in nice English, okay? It tells you if it's an integer or a real, and it tells you what it's for. In this case, it's the lower number to the upper number, and then you can say either what the increment is or just how many you want. And then it tells you details. And details may, for a more important thing, is actually telling you the algorithm and options to the algorithm. And this is really substantive. In this case, it's rather silly. This is so simple, it's inherited from S. And now it gives you value is the output. In this case, it's extremely simple, but often that's a very complicated list of things. Then there's the reference. In this case, it comes from S. There's chambers. Related programs. Often you'll click on those because it's not quite what you want. You want to see what the other ones do. And then the examples. All our help files have examples that work. You cut. You can do it right now. You can take your cursor and grab it and paste in any R console in the world, and it always works. That means that R has a lot of small data sets built into it, that often you need a data set that's appropriate for that statistic. And so they actually bring in their own data sets, which are there, and then it works. And you learn a lot from the examples. So you're always looking at these pages, all the time.
Eric, we have a question from a webcast viewer, going back to when you accidentally summed over the logical array.
Yes.
They want to know how to actually get the sum of.
I'm almost sure that sum A works. Okay. So I will guess to say that this will work. There, I filtered it. Right. That's it. We got it. And you're allowed to do this. You're allowed to embed objects inside of objects in this way. That's what you were trying to teach me before. Right, thank you. Okay, we're now in Roman numeral 3. Let's do some math. This is so easy, I'm not going to spend any time on it. Here are the simple arithmetic operations. They're completely obvious. You use the caret for the exponential, not the double asterisk. And you can do it both with numbers and also with variables, very obviously. Let's do a little bit of astronomy. Yes? Almost no difference at all. It has to do with usage in functions, and inside of functions, equals and double equals have special meaning, but for general command line use, they have the same meaning. So what they say is they prefer that you use this just to train yourself, not to use equals in other circumstances. Some books, almost all books, use the assignment, but some of them use equals. Frankly, it doesn't matter much for most purposes. But the equals and the double equal actually have special meaning. We can try that out. Help, double equal, didn't like that. Help, quote, double equal. There it is. The double equal. Somewhere in here. Do not use double equal for tests in if expressions where you might get a single true or false. Unless you are absolutely sure that nothing unusual can happen, use the identical function instead. So these are subtleties. These are program subtleties on what equal means. This is computer science. It's not astronomy and not statistics. Okay, I defined the speed of light. I defined a Hubble distance. I gave a sequence of 4 redshifts, 6 redshifts, and now I'm looking at the 4th one. I can truncate it, I can round it, I can format it. I find that if you simply say, just ask what's the value of it, it tends to give lots of useless digits. So I prefer to format things, but some of the formats put in quotes, that's scientific format, and I didn't particularly like that either. And actually, there must be enough other people who didn't like it that they actually put in allowing you to do C formatting, and that's also allowed as well. But I actually don't think it formats particularly nicely without some effort. Okay, let's do a little math, sort of silly math. Let's create a sequence from 0 to pi over 2 and take the sign of that sequence and take a look at it. And now let's do our first plot. So we're going to plot an angle from 0 to pi over 2 and the sine, and there is a plot. So that's the default plot. There you are. If you're on Windows, you're on X11. On Linux, you're on X11. If you're on Windows, you're on Quartz. I love Quartz. Quartz is so smart. Look at that. It reformats your axis labels very intelligently, and I often jiggle around until I like it, and then I save it for the OpJ or for use outside, because Quartz is so nice in just formatting things. So that's actually not a very pretty format. So let me now give a fancier format for my plot. First, I used red dots. Secondly, I used solid dots. I put a title on it in bold. I put meaningful axis labels. And this is sort of nicer. And how did I do that? Well, the answer is I also took a log of the ordinate variable. I like to use the character number 20, PCH20. That's filled circles. That says make it 20% bigger. That put an X and Y label on it. That's a main label. That's the size of the label, the size of the title label, and I chose color equal to 2, which ends up to be red. Then I say, okay, let me add something to that. Let me add lines. Whoops, sorry about that. Lines between the points. So I cut and paste my lines. Let's just take a look at it. So I did dashed green lines between the points. Those are actual linear. Those are not. That's not a fit. That's just a straight line between the adjacent points. And I did that with line width of 2, line type of 2, which is dashed, and color green 3. How did I know to use green 3? And the answer is there's 500 colors that have names. And I'll get to that a little later, it looks like. It's not here. And then I say, okay, I'm really pleased with that. I want to save that for my journal or my document that I'm going to share. So I'm going to copy it. This particular function is not well documented. It's documented, but it's not publicized. It's not in most of the tutorials. It's extremely useful to astronomers. Is take my current device, in this case a Quartz device, and copy it to an EPS, encapsulated PostScript file, in my working directory. It's extremely useful. So there's 2 of them that are built in, copy to PDF and copy to EPS. And that's the way you get graphics out of R and put it into your disk in a useful fashion for astronomers. Surprisingly not in the base R, but we could rummage around and try to find something. But it's surprised how this is not considered to be important by the authors of R. I don't know why not.
Question?
Yes?
Is it possible to interact with the figure or not?
No. Yes, there's iPlots. It's a special CRAN package called iPlots for interactive plots. I myself don't do it, but one can, but not in base R. All the graphics are static except for one called RGL, which we might get to. Now, in order to decide or to learn how to adjust your plot axis labels and things, your tick marks, your positioning of your plot panels inside of a larger figure, all of these details are in a help file called PAR. It's extremely commonly used. Until you learn a lot about it, you got to go to help PAR over and over again. It is probably the longest help file I've seen in base R, and it basically does every single thing you'd ever want to do with your plot. So it draws boxes, it tells sizes, it magnifies things, it does colors for the subtitles. It goes on and on. Your fonts, the type of your symbols, your margins, on and on and on. So for beautiful plots, you're looking at PAR quite a lot. In this example and in my book, I do some that are fairly commonly used by astronomers.
So, question for the people among us who are very happy with our matplotlib plotting within Python. Is there just a way to run R from within Python?
Yes.
Do all our plotting like we used to do it?
Yes, believe it or not, there are people in Python who much prefer R plotting, R graphics than Python graphics. Is far more extensive and far more capable. So they're actually doing the opposite of what you just said. Okay, but you can live in Python and you can use R. You can call R, but you got to set up. You got to wrap it. So often the main thing is the arguments coming in. You have to say as numeric and as character. It is a certain clumsiness to the wrapping process. There's RP2, which is less clumsy. Is that correct, Scott? Is it nicer?
I don't know if it's nicer because I just loaded it about 3 days ago.
Okay.
But it works.
But it works. Okay. So,
In IPython, you can really call R functions almost directly, almost seamlessly with these R magics.
okay. R magics? Spell R magics.
Oh, sorry. The IPython is this concept of magics, which are things that extend the Python language. And so within IPython, they made it pretty easy to sort of wrap R. If you have R2 installed, it gets even easier.
Okay.
It's like,
Thank you.
So just look at that. Look in IPython and
Good.
R.
Good. What's your name?
Tom Alcott.
Tom Alcott. Hi, Tom. I thought it might be you. Good. Tom, of course, is a true expert in Python. And are you an expert in R also? Have you done a lot of this connection?
I'm learning.
You're learning. Right. Okay.
That's the first time I've seen it, really.
Good. Good. So you should contribute to that forum that you and I corresponded in to teach others how to do this, because the original way was, let's call it clumsy. I think it's fairly honest to say it's clumsy, but it's getting better as more software is written on both sides of the interface between R and Python. So Tom, it would be really nice if you inform the community how to do that, and maybe that forum or elsewhere would be appropriate. Sir. Okay.
Quick comment. Tom, if you could just add a note in our Google Scratch space so it'll say that.
Yeah, I just did this. If you Google IPython and RMagic are one word, there's a web page that comes up and shows you how to do it all.
Okay.
I'll put that in the forum.
Thank you. Okay. Comment? Comment.
Well, so there must be several ways of reading in an ASCII file with multiple columns and
Yes.
assigning them to.
Yes. In fact, we'll get to that in a minute. Yes. Yes. It's very good at reading ASCII, but it also reads binary. And not much else. You can have a formatted read as well. Okay, so we made our first plot. Now, I don't think I'm going to spend much time. I remember the purpose of this. The purpose of this was to show how to write some functions. So here is a little more. This is Planck numbers of omega mass and omega lambda, and here is a distance function that is a standard formula from lambda CDM cosmology. And what I've done here is to show you, you say, let something here equals or be assigned to a function, the word function is a function, function, parenthesis, and these are the inputs to the function. And then you use curly bracket. And then you use the inputs and do some calculation with them. And then you close curly bracket. And this doesn't actually evaluate it at the time. It just sets up what you and I would call a subroutine. So I've written a subroutine, a rather short one. Now I'm going to write another subroutine called luminosity distance. Lumdist. And this function says, I'm going to call something dist that's going to come out. I'm going to return it. That uses some constants. It's now going to integrate this function from 0 to the value of the input, which is redshift. And I got to say, help integrate to find out what comes out of integrate. And I find that if I actually want to know the number of the integration of that function, I actually have to say integrate $ value. And I'll tell you in a minute what the $ does. It goes inside of lists. So this is now a function that uses another function. See how that one there is not a constant? That one is another function. And then it does a calculation. In this case, it runs a function called integrate. And it comes out. Just one sec. And then I'm now going to run it. Lumdist. And I'm going to put in a redshift. And I get an answer. And I think in megaparsecs. And I do it again. And it's nonlinear. So I increase by a factor of 10. I do not increase by a factor of 10 the luminosity distance. Yes, sir?
I was a little confused by the function definitions. So you got E.H0 defined as function redshift.
Yes.
Is there a name of a function? Oh, sorry. So
This is the name of the function. From now on, E.H0 is going to be defined as this essentially operation.
okay.
And so when I use it later on, it's
You're
being...
not giving it any, you're not giving any parameters to E.H0.
No, at the moment it uses conceptual parameters. It's only later on when I actually implement it, does it actually plug in a number, do the calculation. In this case, it plugged it in here, and then it used it in this integral.
But it's more like a macro, because you really don't pass all the argument used in the function, because essentially omega underscore n and omega underscore lambda are defined at the top level. So it's
Okay.
a macro, it's not a function. Because the namespace
Yes.
is shared with the name
Yes.
at the top level.
Okay, the word function is a special thing in R. It's not English. It's what I think of function as subroutine. That's my personal way of thinking of it. So it doesn't necessarily mean what the word function means elsewhere. So I'd like to do help integrate to see what this is where I actually did a calculation that wasn't sort of arithmetic. So in this case, I have to put in the first input to the function called integrate, which does adaptive quadrature of one variable over a finite or infinite interval, is I need a function at the beginning. So that's why I needed to define E.H0 ahead of time, because this particular function needs a function as its input, then the upper and lower, and then I can adjust the calculation. And it returns whatever I call it, but these then are accessed through the $. It's sort of a section of the list that comes out. The word list here is technical. A list, an R list, comes out of it, and the value is the final estimate of the integral. Okay, it now discusses some things. It ends up it's based on QuadPack, which is an old code from netlib. And here's a reference to it from the 1980s. So, in my opinion, these things are important. It's not, I mean, I wouldn't do it for something as simple as this, but it's not unlikely that I might put this reference in my AppJ paper. mean, this is the reference to the algorithm, to the procedure. When I do something sophisticated in R or CRAN, I want to inform the reader what I'm doing. And I can say, oh, well, I use this code version 10. But it's also useful to say, there's a book or an article, a technical article or book. That's where it's from. And R is just an implementation of this method. In this case, QuadPack, a 30-year-old applied mathematics package that I assume has good heritage. Let's take a look at it here. I'm going to say STR for structure and look at lumdist. That's not quite what I wanted. Let me do structure. No, this is not going to work. That's funny. I thought I would get a little more information out of that, but I didn't. Okay. Okay, so that was an astrophysical calculation using functions. And of course, when you really do your coding, you're coding inside of functions. You're making lots of functions and doing things. Okay, I'm not going to read these help files now, but I'm going to be using several functions, one called sample and rnorm and rbind. And let's just take a look at what I'm going to do. I'm going to create two variables of 500 elements each, called x and y. The first one is just going to be a sequence. Well, I'm going to first make a regular sequence from almost 0 to 3 of 500 numbers, and then I'm going to randomly select from it. So this is not, so it may not be evenly spaced, and then I'm going to just take this arithmetic and make this nonlinear function out of it, and I'm going to add a random normal. The word normal means Gaussian. A random Gaussian noise with this mean and with this standard deviation. But the standard deviation itself depends on x. This is called heteroscedasticity. And you'll see in just a second that this adds a sort of a nonlinear scatter to my x and y. So I have a nonlinear function with nonlinear scatter of x and y. So first things to do is to take a look at these x's and y's as univariate objects. In this case, it gives me these means and medians and quartiles. I can look at the structure of it. It's very simple. It's just 500 numbers, and it gives me the first few of them. I can bind them together. I already had shown you C bind for column bind. This is now R bind for row bind, so I can concatenate things by row. And there we go. I've made a little temporary little thing. And the row binds and column binds are very useful for putting things together. So now I'm going to make some plots. I'm going to make what are called box plots that are essentially plots of those same numbers in the summary. And here are the box plots for x and y. And you can see x is a very symmetric variable from 0 to 3. And r is a very asymmetric variable from that with all sorts of weird outliers and asymmetries to it. That's the median, 25th and 75th quartile. These are appropriately made whiskers, and if it's Gaussian, there should be few, if any, outliers, and they should be symmetrical. The notch is proportional to it tells you the approximate uncertainty of the median, and the width tells you the scale to the sample size. So this is a box plot. Box plots are rarely used in astronomy, but very commonly used in other fields. And they're just convenient. They're not amazing. They're just really convenient.
So is this choice of the quantiles default in the box, or you have to somehow say it? How to
No, this is defaulted, but I can do help box plot, and I can change almost anything. Box plots, this default was decided by John Tukey in the 1960s. Okay, is it right? There's no right or wrong. It's just a convenient, simple visualization of univariate data. And once again, I can copy this to a device. box.eps is now on my disk, ready for communication to others. Another commonly used histogram, univariate plot is a histogram. Let's look at the Y one, which is a little unusual. So there we are. In this case, I colored it yellow. And you can see it's asymmetrical. How do you know how many breaks to put in? The answer is you don't know. You can use, they get 3 defaults, which have some theorems behind them, but frankly, it's all guesswork. And you'll hear from me later that histograms are not advised for inference because there's a lot of guesswork involved in deciding on the bin widths. Here's a way of saying, of asking the question, is this similar to a Gaussian distribution or a normal distribution, as they would say? And it's called a quantile plot. This is a theoretical, in this case, is a normal quantiles, and these are the sample quantiles, and if they're roughly Gaussian, they would lie on a straight line. In this case, they're far from, particularly on the upper end, it's asymmetrical. And this is actually fairly useful. I personally use it all the time for residuals of regressions. If my residuals are not Gaussianly distributed, then I have non-Gaussianity in my problem, and maybe I don't have a sufficiently elaborate model. Another common univariate plot is the empirical distribution function, empirical cumulative distribution function, ECDF. And here it is. It's a step function that goes up 1 over 500 every time there's a point. The step function for x is very boring because I made it boring. The step function for y is a little more interesting with some slow growth and then a rapid in the middle and then a long tail over there. And I can add text to any figure using the text commands. I can annotate it. There's also a legend command and others like that. In this case, I just labeled my curves. And I could save that to disk as well. I think the only interesting thing here, maybe not the only interesting thing here, is I used add equals